So I begin in the introduction by claiming that I can invalidate lambda CDM, or expanding the Big Bang. I can invalidate the Big Bang theory by invalidating the core assumption in lambda CDM, which is homogeneity. Now, homogeneity is part of what's called the cosmological principle. Later in the book, I get into this, but the cosmological principle is kind of like this foundational way of formulating the universe with general relativity. And what lambda CDM does is it assumes homogeneity throughout the entire universe. And what that means is that it's assigning the same mass density to all locations in the universe. This is obviously false. Even the experts say that it's false. Even Einstein knew that it was false. It's just an averaging. It's just a way of moving forward with the equations. But it's wrong. They know it's wrong. You and I know it's wrong. It's just wrong. The way to do it is have a density profile. Now, you can say this is crazy, but it's the only way to do it. Like, think logically. Mass density is a scale-dependent variable. This phrase, this sentence probably appears 100 times in my book. This is the most important thing. It is a scale-dependent variable, which means it depends on the size of the volume. So if you choose an enormous volume, you're going to have a very low density. If you choose a small volume, you're going to have a high density. That is always true in this universe. Now that you can just choose small areas, like you can choose something the size of a star, or the size of a planet, or the size of a marble. If you choose volumes that size, then you can have a dramatic range. Okay? But if you choose volumes that have a radius of, say, 1 megaparsec or 100 megaparsecs, you're not going to have much of a range. It's going to range from scale to scale, but not from. So, in other words, if you have a volume, let's say a basketball-sized volume of space, and we can just randomly sample throughout the universe, the density for that basketball-sized object is going to range dramatically, because you can check, say, an empty part of the universe and come up with a very low density for that basketball-sized volume. But if you check a black hole, it's going to be very high density. Now, if you increase the radius of that basketball to, say, 100 megaparsecs, almost every single, well, not almost, every single region you check will have an nearly identical mass density. You're not going to have much of a range. And the reason is that as you increase the scale, mass density decreases. And it's just a fact of math and geometry and the definition of mass density. There's no way of getting around it. Now that you understand that, we can move on to gravitational redshift, because that fact changes the formulation of the universe in cosmology using general relativity. We're just in the introduction, so I'll explain why later. But for now, understand that you have to have a density profile. In other words, you're starting from coordinate 0. So you can put, in general relativity, you can place your coordinates anywhere. You can start at 0, the 0 point, the center of your metric can be placed in the center of the sun. It can be placed in the center of the galaxy. It can be placed in the moon. It can be placed at a random location. It can be placed anywhere. That's the whole point of general relativity's setup, is that you can the coordinate choice doesn't change the physics. It may change how your interpretation and perspective and all that and the solution. There's a lot of context involved, but it doesn't change the physics of it. And so you can place your coordinate choice anywhere. And R, as you increase, or as you go along R, if you just sample a position along R, which R is the infinite radius of your coordinate system, okay? That is, your metric continues out forever, and the R is whatever point you want to measure from the center of your metric. And now, if you do that, and then take the sample for the mass density, you will find that it decreases along R. It has to decrease along R. It cannot stay the same, okay? It must decrease along R. That's the point I'm trying to make with this whole little section right here. Now, you can have it decrease to 1 over R, 1 over R squared, or 1 over R cubed. If you do 1 over R cubed, you're basically doing the Schwarzschild metric, which you're basically saying this is a ball in an empty universe, and R continues forever to infinity, and there's no other objects in the universe. And so that's not real. That's just imaginary for you to define that object that you're talking about, because you're trying to find a starting point. And so you place, say, the sun or the earth. If you place the earth in an empty universe, then the surface gravity of earth is 9.8 meters per second squared. And so you can do calculations and find what it would be if there was no other objects in the universe affecting that object. But that's not how we want to do cosmology, because obviously there's lots of objects in the universe, so we want to include them all. And presumably, if you keep going, you're just going to see more stars. Like, no matter where you go, there's going to be stars. So we're left with only two options, 1 over R and 1 over R squared. Now, 1 over R can be aligned with the Hubble shift, the cosmological redshift. Okay, the cosmological redshift is why they think the universe is expanding in the very first place. And 1 over R produces a gravitational redshift that aligns with the Hubble shift. 1 over R squared does not. You would have to do some sort of combination of gravitational redshift and Hubble shift. It's still linear dependent, but as you increase with R, the amount of gravitational redshift decreases. So, 1 over R it is. Now, I go into gravitational redshift also, and I honestly don't like this section that much, but it does clarify some things among experts. There's a lot of people that would have, say, PhDs in physics, but they maybe only had one class in relativity. And they think that the time dilation explanation of gravitational redshift is how it works. Or they think that it's a photon loses energy as it leaves an object. And, I had to clarify that it's the null geodesic is how you do it. And so you want to do the 4 velocity and the 4 momentum. This is how you do it. So I'm not going to go into detail in this book on very specifics. I'm not Wald or Meissner or anybody like that. I'm just saying I can reference to them to say that this is actually the appropriate way to do it, is the null geodesics. That's actually the right way. And then you would apply the cosmological model on top of that if you wanted. But you have to first include the geometry of the area you're talking about. That is important. You can't just assume the object is alone in the universe, because all objects are connected into this unified manifold that is general relativity. And I also talk about how Newtonian potential is kind of this, it's like a good way to communicate about it, but it's not. It's like the sun doesn't have a specific potential, okay? The sun's gravitational potential depends on your location. If you are a black hole, the sun's gravitational potential is nothing compared to you. Like, you'll just eat it. Like, it's relativity is confusing because it is relative. There are no absolutes in relativity. You have to compare things to other things. And the universe is not empty. We'll get into more of that. I think that's probably good enough. This is basically the introduction. Let me explain these graphics here, though. So I have two graphics with 3 observers and a star in both of these. Now, this star has a cloud of dust right here around it. And like I explained, that observer 1 has the most amount of gravitational redshift. So if observer 1 is measuring the light from this star, observer 1 will see the lowest frequency compared to observer 2 and observer 3. And that's because they are closer to this star. And so the relative time, the relative geometry for this null geodesic, for a geodesic from the star to the observer, is not as dramatic. Like, distance makes the relative nature more dramatic, and so there's a larger redshift. Now, in this one, I've added more dust. So now there is an enormous cloud of dust, so much so we don't even know the outer boundary of it, and the observers are buried inside of it. So now this is tired light. This is the equivalent to tired light because now the amount of gravitational redshift is proportional to the distance, because the distance is how you determine how much of the dust impacts the geometry. And so observer 1 still sees the lowest frequency. Observer 2 is the second lowest frequency. And observer 3 sees the highest frequency. And that's because the gravitational redshift increases with distance. And so this is how we align the 1 over r with the Hubble redshift. All right. Look out for the next video that comes out, Chapter 1. It's amazing. It's an amazing chapter.